Hello, and welcome to Cloud OnBoard, Architecting with Google Kubernetes Engine. Thank you for tuning in. This is your first step on the learning journey toward becoming an expert Google Cloud professional. My name is Suzanne Haas, and I'm a Google Cloud trainer. And if you have any questions throughout today's event, please feel free to enter them into the text box below the video. We have Google experts on standby to answer your questions live. Throughout today's event, you'll see quiz questions popping up on the right-hand side. So, please participate to share your knowledge of what you've learned so far. This session is being brought to you by Google and Fastlane. Fastlane is a globally authorized learning partner for Google and many other large technology providers. We have offices in 45 countries and support many enterprises with global skilling initiatives. We also augment our Google deliveries with additional service offerings such as mentored installs and migration support. And one of our key service offerings is our Expert for Hire program. The Expert for Hire program is a way of extending the value of any training class we provide by leveraging that same instructor to support you on additional projects or other needs relevant to the class topic. And furthermore, Fastlane has great experience in the development of full learning platform systems, integrated with great content from vendors like Google. Fastlane also recently was named the most innovative training partner for 2019. And Fastlane can bring you Google Cloud Platform training across all roles from architecting and engineering to DevOps and detailed training on Anthos. Lastly, by attending this Cloud Onboard experience, Fastlane is now offering you an exclusive offer. Contact us for more information about this offer, which includes a discount on private class deliveries as well as a $400 Amazon gift card. Now, below, you can see great follow on courses to this Cloud Onboard experience. So visit us at fastlaneus.com for more information. So, welcome to the What is Kubernetes section. In this section, you'll learn what containers are and what their benefits are for application deployment, and how containers are configured and built, and what functions container management solutions like Kubernetes provide, and what the advantages of Google Kubernetes engines are compared to building your own container management infrastructure. So let's start by looking at an overview of Kubernetes and an introduction to containers, and the key features of containers, as well as their advantages for application deployment. You'll learn about Google's Cloud Build and see how to use it to build and manage your application images. Now, when it comes right down to it, Kubernetes was created to automate most of the tasks associated with deploying many clustered services across many infrastructure components. Now, not very long ago, the default way to deploy an application was on its own physical computer. And to set one up, you'd have to find physical space, power, cooling, provide network connectivity for it, and then install an operating system as well as any software dependencies, and finally your application. And if you needed more of anything, well, you had to add more computers. And each computer often had only a single purpose. For example, running a database, or a web server, or content delivery. Now, this was not very efficient use of resources, and it also wasn't very portable, because applications were typically built for a specific operating system and sometimes even for specific hardware. Then, virtualization helped by making it possible to run multiple virtualized servers and operating systems on the same physical computer. Now, VMware were leaders in virtualization, and they achieved resource sharing by implementing what was called a hypervisor as the software on the physical server to break all those dependencies of the operating system on the underlying hardware, and also allow virtualized machines to share the resources of that hardware. Virtualization allowed for more efficient use of resources, less time for deployment of solutions, and also some portability, because virtual machines can be imaged and moved around if you want. However, the application and all its dependencies and operating system functions are still bundled together in a virtual machine. And it's not easy to move a virtual machine from one hypervisor type to another. And every time you start up a VM, well, it's like a machine. Its operating system takes time to boot up. Now, a more efficient approach is to virtualize just the application and its dependencies instead of the entire machine or even the entire operating system. So, just the user space, which is all of the code that rides above the kernel, including the applications and their dependencies. So, this is what it means to create containers. Containers are isolated user spaces for running your application code. Now, containers are lightweight because they don't have to carry a full operating system, and they can be created and shut down very quickly because you're just starting and stopping an operating system process, not booting up the entire VM for each application. Containerization is the next step in the evolution of managing your code. So now you know what a container is. It's a delivery vehicle for application code. You develop your application code in the usual way on your desktop, your laptop, your servers. And the container allows you to execute your final code on VMs without having to worry about software dependencies, like application runtimes, system tools, system libraries, and settings. You package your code with all the dependencies it needs, and then the engine that executes your container is responsible for making that available at runtime. Now, containers are application centric, and they allow developers to safely make assumptions about all that underlying hardware and software. So, this appeals to developers because they don't have to worry about the rest of the system. So, you don't have code that works on your laptop, for example, that you develop the code on and then doesn't work in production. The container is going to be the same, and it runs everywhere. And finally, containers allow the operating system to scale and upgrade components for an application without having to affect the application as a whole. An application and its dependencies are referred to as an image. A container is simply running an instance of an image. And if you make incremental changes to the container based on a production image, well, you can deploy it very quickly. This speeds up your development tremendously. Now, you need software to build container images and to run them. And Docker is an open source technology that allows you to create and run applications in containers. But it doesn't offer a way to orchestrate those applications or the resources they use. Now, because each container has its own writable container layer, and all the changes are stored in this layer, multiple containers can share access to the same underlying image and yet have their own data state. Now, the diagram here shows multiple containers sharing the same Ubuntu image. Now, when you build a container, instead of copying the entire image, it creates a layer with just the difference. And when you run a container, the container runtime pulls down the layers that it needs. Now, when you update, you only need to copy the differences. So this is a lot faster than spinning up and running a whole new virtual machine. Now, in this lesson, we'll introduce Kubernetes and how it helps you automate deployment, scale, and manage your containerized applications. All right, so say your organization has really embraced the idea of containers, and because containers are so very lean, your coworkers are creating them in numbers far exceeding anything you ever did with virtual machines. And the applications running in them need to communicate over a network. But hey, wait a minute, you don't have a network fabric that lets containers find each other. You need help. So how do you manage your container infrastructure better? Well, Kubernetes is an open source platform that helps you orchestrate and manage your container infrastructure on premise or in the cloud. So, what is Kubernetes? Well, it's a container management environment that automates the deployment, scaling, load balancing, logging, monitoring, and other management features of containerized applications. Google originated it and then donated it to the open source community. Kubernetes supports declarative configurations, which allow you to describe the state you want to achieve instead of having to issue a series of commands to achieve that state. Declarative configurations saves you a lot of work. Kubernetes' job is to make sure that the deployed system conforms to whatever the state is that you declare. And Kubernetes also allows imperative configuration, in other words, issuing all those commands. But that's usually for quick temporary fixes or maybe as an admin tool in building up a declarative configuration. Now remember, deploying containers at scale is going to be different. And a fundamentally different way of managing applications is going to require different tooling and abstractions. Google Kubernetes Engine is an enterprise-grade platform for containerized applications. But let's pause for a second and talk about what you get when you set up a container engine cluster. Now, the whole process takes about 3 minutes on average. You click a button, and 3 minutes later, you get your cluster, including a Google Kubernetes architecture managed by Google with a Kubernetes API, Kubernetes control plane, multiple pods, and nodes automatically deployed per your specification. Now, in simple terms, you can think of Kubernetes as the operating system for your fleet of hosts that make up your compute infrastructure. Kubernetes provides features similar to the OS for a host, and it allows you to schedule your workloads across this entire fleet. You just specify what you want to run and how many copies you want to run of the workload, and Kubernetes finds the right place to run the workload and then monitors the state of the workload to make sure that it meets your specific desired state. Now, in this lesson, you'll learn about Google Cloud's managed service offering for Kubernetes called Google Kubernetes Engine, or GKE for short. And why do people choose it? What if you begun using Kubernetes in your environment, but the infrastructure has become a burden to maintain? Is there anything within Google Cloud Platform that can help you out? And the answer is absolutely yes. GCP offers managed Kubernetes solution called Google Kubernetes Engine, or GKE for short. Now, as mentioned, Google Kubernetes Engine is a managed Kubernetes service that runs on a Google infrastructure. GKE helps you deploy, manage, and scale Kubernetes environments for your containerized applications on GCP. And more specifically, GKE is a component of the GCP compute offerings, along with other offerings like, say, Compute Engine, App Engine, and Cloud Functions, as well as other managed services. So it makes it easy to bring your Kubernetes workloads into the cloud. So this is along with other offerings like Compute Engine, App Engine, Cloud Functions, and other managed services. Now, GKE is fully managed, which means you don't have to provision the underlying resources. GKE uses container-optimized operating systems to run your workloads that are managed and maintained by Google and are optimized to scale very quickly. When you use GKE, you start by directing the service to create a Kubernetes system called a cluster. The virtual machines that host your containers in GKE clusters are called nodes. And if you enable GKE's auto repair feature, the service will check the health of each node in the cluster and then repair them automatically. GKE supports scaling the cluster and seamlessly integrates with Google Cloud Build and Container Registry, which allows you to automate your deployment using private container images you've securely stored in Container Registry. GKE also integrates with Google's Identity and Access Management to allow you to control access and permissions for team members and other users. And GKE integrates with Stackdriver monitoring to monitor your application's performance and is integrated with Google Virtual Private Clouds to make use of GCP's networking features. And the GCP console provides insights into GKE clusters and their resources and allows you to view, inspect, and delete resources in those clusters if you need to. So in this last lesson, we're going to talk about available computing options. Previously, we introduced choices for running compute workloads in GCP, and now that we know more about how containers work, we can compare these choices in greater detail. So in simple terms, you can think of Docker containers, or any other containers for that matter, as processes running in a jail created by control groups and change root. The container is running in isolation from all other processes on the host. And Docker container images can be thought of as a packing format that allows you to bundle your application and all of its dependencies, including things like libraries and tools and utilities and things like that it needs. You can pretty much add anything to the image for the operating system except the operating system kernel. The kernel has to be shared with the host machine. Container registries are repositories for you to post and share your container images. And the images have to be stored in an accessible registry for Dockers to be able to pull them down and download them. So looking at all these options that you see here, you might be wondering, which compute service should I adopt? Well, a lot depends on where you're coming from to begin with. If, for example, you're running applications on a physical server hardware, the path of least resistance will be to move into Compute Engine. And if you're running applications in long-lived virtual machines, well, again, you'll find that Compute Engine is probably the quickest GCP service for getting your applications into the cloud. Now, if you don't want to think about operations at all, then App Engine and Cloud Functions are great choices. In fact, both Compute Engine and App Engine can launch containers for you. Compute Engine will accept a container image from you and then launch a virtual machine instance containing that image, as well as scale and manage the resulting VM. And App Engine Flexible Environment will accept a container image from you and then run it in the same no-ops environment that App Engine delivers for your code. If you want more control over your containerized workloads and denser packing, well, now that's what GKE is designed to address. You can also choose Cloud Run to run stateless containers on managed compute platforms. And of course, if you're already running Kubernetes in your on-premise data centers, then moving to GKE is a great choice because you can import both your workloads and your management approach. So let's take a brief quiz on the concepts we've learned so far. Kubernetes was created to automate most of the tasks associated with deploying many clustered services across many infrastructure components. So what are some of the capabilities that Kubernetes provides? Well, now, if you chose all of the above, you'd be absolutely correct. So here's the next question. You need a solution for deploying applications and you want to deliver them in lightweight, standalone, resource-efficient portable packages. Which of these choices is the best solution? And if you chose containers, you'd be correct. And finally, when deploying a containerized application, which of the following Google Cloud platforms would you choose to provide the most control over your containerized workloads? And if you said Google Kubernetes Engine, you'd be right on the mark. So this concludes the What is Kubernetes Engine section. And in this section, you learn how to identify the challenges we're trying to solve. And you learned about creating a container using Cloud Build, storing a container in Container Registry, and comparing and contrasting Kubernetes and Google Kubernetes Engine features. Welcome to the Kubernetes architecture section. In this lesson, we're going to talk about the parts of Kubernetes, as well as the philosophy Kubernetes implements. Things like, how does Kubernetes expect you to tell it what to do? And what choices do you have for describing your workloads? That's the theme of this section. Let's begin by looking at Kubernetes concepts. So that we can understand how Kubernetes works, we'll discuss two closely related concepts that you'll need to understand. And the first is the Kubernetes object model. The second is the principle of declarative management. Now, everything Kubernetes managed is represented by an object. So be aware, Kubernetes expects you to tell it what you want it to do and what you want the state objects to be. And then it will work to create that object state and keep it by using what is called a watch loop. So here we're going to learn about Kubernetes objects and the control plane and how to deploy a Kubernetes cluster and pods using Google Kubernetes Engine. We're also going to learn how to view and manage objects. Now, officially, a Kubernetes object is defined as a persistent entity that represents the state of something running in a cluster along with its desired state and its current state. Objects represent containerized applications, along with the resources that are available to them and the policies that affect their behavior. A pod is a basic building block in our Kubernetes model. It is the smallest deployable Kubernetes object. And a pod embodies the environment where the containers live. And by the way, they can contain more than one container. If there's more than one container in a pod, they share resources like networking and storage. And Kubernetes assigns each pod a unique IP address so that the containers inside the same pod can communicate internally. So let's suppose we give Kubernetes a desired state consisting of I want 3 Nginx pods, and we want them to be kept in an always running state. Now, we would do this by telling Kubernetes to create and maintain one or more objects to represent the pods. And if our declaration of 3 Nginx containers is completely new, the current state is not going to match our desired state, namely up and running. So when Kubernetes compares the desired state to the current state, it's going to see that the number of desired pods to be kept running should be 3 and that none are currently running. So Kubernetes will remedy the situation by launching 3 pods and will continue to monitor and correct the status of the pods as needed. Now in this section, we'll examine a Kubernetes cluster part by part and explain each piece as we go along. So let's take a look at the corresponding and cooperating processes that make a Kubernetes cluster work. First and foremost, your cluster needs computers. One of the computers is going to be called the master, and the others are simply called nodes. The job of a node is to run the pod, and the job of the master is to coordinate the entire cluster, which it does using the control plane. So let's talk about control plane components first. Now, the single component you interact with directly is called kubeAPI server, whose job it is to accept commands to view or change the state of the cluster, including launching your pods. You'll use kubecontrol command frequently to connect to the kubeAPI server, and any query or change in the cluster state needs to be sent to the kubeAPI server. etcd is the cluster database, whose job it is to reliably store the state and configuration of the cluster. You never interact directly with etcd. Instead, kubeAPI server interacts with the database on behalf of the system. So the kube scheduler is responsible for scheduling pods onto the nodes. Now to do that, it evaluates the requirements for each individual pod and then selects the node most suitable. But how does kubescheduler decide where to run a pod? Well, it knows the state of all the nodes, and it will also obey any constraints that you define regarding where the pod can run. So these constraints are based on hardware, software, as well as policies. Kube Controller Manager has a broader job, and that's to continually monitor the state of the cluster through the kubeAPI server. And whenever the current state of the cluster doesn't match the desired state, then of course the kube controller manager will attempt to correct the situation. Cooperating processes are what makes the Kubernetes cluster work. And on each individual node, there are control plane components running as well. For example, each node runs kubelet, which you can think of as a Kubernetes agent on each node. When the kubeAPI server wants to start a pod on a node, it connects to that node's kubelet. Kubelet uses the container runtime to start the pod, monitor its lifecycle, and report to the kubeAPI server. Now, the container runtime is the software that knows how to launch a container from a container image. kubeproxy's job is to maintain the network connectivity amongst the pods in the cluster, which it does using firewall capabilities. So as you can see from the diagram we just looked at, the control plane of Kubernetes has a lot of components, and setting up a Kubernetes cluster by hand would be a lot of work. So let's take a look at the concepts specific to Google Kubernetes Engine and see how to make things easier. Fortunately, in Kubernetes environments, there's an open source command called kubadmin that can automate much of the initial setup of the cluster. But if a node fails or needs maintenance, then a human administrator still needs to step in and respond manually. So you can see why a lot of people like the idea of a managed service for Kubernetes. In Google Kubernetes environments, GKE manages all the control plane components for us. It gives us an IP address to which we send all our Kubernetes API requests, but GKE is going to take responsibility for all the provisioning and managing of the master infrastructure behind that address. It also abstracts away the need to have a separate master. Instead, those responsibilities are performed by Google Cloud Platform. So you're not billed for a separate master node. So let's talk about nodes. In Kubernetes environments, the nodes are created externally by a cluster administrator. GKE automates the process for you. It launches Compute Engine virtual machine instances and registers those as nodes. Now, you can manage the node settings directly from GCP console. And though you're billed for the allocated time for the nodes, you're not billed for having a separate master node. You can select multiple machine types by creating multiple node pools. Now, a node pool is a group of nodes within a cluster that share the same configuration, such as memory or CPU. And they provide an easy way to make sure that workloads running on the hardware are running on the correct hardware within your cluster. Node pools are specific to GKE rather than Kubernetes. And you can enable automatic node upgrades, node repairs, cluster auto scaling at the node pool level. Now, by default, the cluster is launched in a single GCP compute zone with 3 identical nodes in one specific node pool. The number of nodes can be changed during or after the creation of the cluster. And adding more nodes and deploying multiple applications will, of course, improve an application's availability, but only up to a certain point. So, what happens if the entire compute zone goes down? Well, you can address this concern by using what is called a regional cluster. Regional clusters have a single API endpoint for the cluster. However, its masters and nodes are spread across multiple compute engine zones within the region. Now, regional clusters make sure that the availability of the application is maintained across multiple zones within a single region. And the availability of the master is also maintained so both the application and management functionality can withstand the loss of one or more zones as long as it isn't all of them. By default, a regional cluster is spread across 3 zones, each containing 1 master and 3 nodes. These numbers, of course, can be changed. But once you build a zonal cluster, you can't convert it into a regional cluster or vice versa. The entire cluster, which includes the master and all its nodes, are hidden from the public. Cluster masters can be accessed by Google products such as Stackdriver through an internal IP address, and they can also be accessed by authorized networks to an external IP address. Now, in addition, nodes can have limited outbound access through private Google access, which allows them to communicate with other GCP services like Google Container Registry without needing an external IP address. So next, let's talk about Kubernetes object management. All Kubernetes objects are identified by unique names and unique identifiers. So let's go back to our previous example, in which we wanted 3 Nginx web servers running at all times. The simplest way would be for us to declare 3 pod objects and specify the state for each, as specifying that the pod has to be created using an Nginx container image. So let's take a look at how we're going to declare this. Now, as you can see here, the objects you want Kubernetes to create and maintain are defined with what are called manifest files. Now, these are ordinary text files, and you can write them in YAML or JSON format. YAML is more human readable and less tedious to edit than JSON files, and it defines a desirable state for a pod. So that would include its name, a specific container image for it to run on, and those types of things. Now, your manifest files have certain required fields, such as API version, which describes the Kubernetes API version to be used. And kind identifies the kind of object you want. In this case, it'll be a pod. And of course, we have metadata to help identify the object using it, such as name, unique ID, and optional namespace. You can define several related objects in the same file, fortunately, and it is a best practice to do that because it's a lot easier to manage one file than a lot of them. The Kubernetes default scheduling algorithm will automatically spread a workload evenly across the nodes available in a cluster. So we could get a situation that looks like this here, which looks great, doesn't it? But imagine if you want 200 more Nginx instances, managing 200 more sections of your YAML file to declare these would be really inconvenient. And here's another consideration. Pods do have a life cycle. They don't heal or repair themselves and are not meant to be run forever. They're designed to be what is called ephemeral and disposable. So for these reasons, there are better ways to manage what you run in Kubernetes than to specify each individual pod. So how do you tell Kubernetes to maintain the desired state of your 3 Nginx containers? Well, you would need to do this to maintain availability. And you do this by declaring a controller object whose job it is to manage the state of the pods. Now, some examples of these objects would be things like deployments, stateful sets, daemon sets, and jobs. Now, it is quite likely that you'll be using a single cluster for multiple things that you and your colleagues are working on. And you might be wondering how you can maintain resource quotas based on project or team, and that's going to be essential. So each Kubernetes cluster is associated with a GCP project, which is to say a set of resources and services that are allocated for use, and to which identity access management policies can apply, and of course, for which you're built. Namespaces are important for tracking resources, and there are 3 initial namespaces in a cluster. The first is the default namespace for objects with no other namespace defined, and your workload resources use this namespace by default. Then there is the kube system namespace for objects created by Kubernetes system itself. And the third namespace is the kube public namespace for objects that are publicly readable to all users. Now, kube public is a tool for disseminating information to everything running in the cluster. So let's pause and take a brief quiz on the concepts you've learned so far. What is the difference between a pod and a container? Well, if you guessed that a pod can contain 1 or more containers, you would be correct. So here's the next question. True or false? Regional and zone GKE clusters can be set up as private. And the answer is true. And finally, what type of file is used to define objects? And the answer is, well, none of these. So this concludes the Kubernetes architecture section, and you learned about Kubernetes operating philosophy. Every item under Kubernetes control is represented by an object. Kubernetes tries to keep the state of the cluster matching the state you've declared that you want. And you've learned about the control plane components that make up Kubernetes. You also learned that GKE Manager Cluster implements the master for you behind the scenes. To tell Kubernetes you want this state of your cluster to be, you create manifest files, and typically you'll build them in YAML format. And these files name and describe the objects that you want Kubernetes to keep alive and healthy. So next, let's focus on running Kubernetes on Google Cloud Platform. In this module, you'll learn how GKE clusters are powered by the Kubernetes open source cluster management system, through which you can interact with your cluster, of course. And you can use Kubernetes commands and resources to deploy and manage applications, perform your admin tasks, set your policies, and monitor the health of your deployed workloads. Google Cloud offers server-side load balancing so you can distribute incoming traffic across multiple virtual machine instances. And load balancing uses forwarding rules to match certain types of traffic and forward it to the load balancer. For example, you can have forwarding rules that match TCP traffic port 80, which then forwards the traffic to a load balancer, which subsequently directs it to a healthy VM instance. Now, Google Cloud Load Balancing is a managed service, which allows you to scale your applications to support heavy traffic and detect and automatically remove unhealthy VMs using health checks. It can also automatically re-add instances that become healthy again and route traffic to the closest virtual machine as a managed service. Load balancing components are going to be, of course, redundant. And if a component fails, it's automatically restarted or replaced immediately. Now, the diagram here illustrates a common use case, how to use an external as well as internal load balancing. In this example, traffic from users in San Francisco, Iowa, and Singapore is directed to an external load balancer, which distributes that traffic to different regions in a Google Cloud network. Now, the internal load balancer takes the traffic that's been delivered to the US Central region and distributes it between US Central 1A and US Central 1B zones within that region. Compute Engine offers auto scaling to automatically add or remove VM instances from an instance group based on increases or decreases of load. Auto scaling lets your apps gracefully handle increases of traffic and then reduces the cost when the need for the resources is lower. So you define an auto scaling policy, and the auto scaler performs automatic scaling based on the measured load. And your policies can include elements such as CPU utilization, load balancing serving capacity, and other monitoring metrics. Google Cloud uses the following components to build application instances, including a compute engine instance template, which is used to create each instance in an instance group. Cloud storage, which is a bucket used to host the startup script and other script files for the machine instance. A compute engine startup script, which of course is the startup script that installs the necessary code components. Now, the startup script is installed and starts automatically when the instance starts. And when the startup runs, it in turn installs and starts the code on the instance. And then, of course, writes values to the monitoring metric. The compute engine instance group, which is the instance group that auto scales based on the cloud monitoring metric values. And the compute engine instances themselves, which are a variable number of compute engine instances to be used for the application. And of course, we have custom cloud storage metrics, which are the monitoring metrics used as input values for compute engine instance group autoscaling. So let's talk node pools. A node pool is a group of nodes within a cluster that all have the same configuration as we mentioned previously. For example, you might create a node pool on your cluster specifying the use of SSDs or a minimum amount of CPU, a specific node image or instance sizes or machine types. Custom node pools are really useful when you need to schedule pods that require more resources than other pods, such as maybe more memory or more disk space. Node pools use node config specifications. The node in the pool has a Kubernetes node label, which has the node pool's name as a value. And the node pool can contain only a single node or many nodes, depending on what you need. And you can create and upgrade and delete nodes individually and node pools individually without affecting the entire cluster using the gcloud container node pools command. You can't configure a single node in a node pool. Any configuration changes affect all the nodes in the node pool. And when you create a cluster, the number and type of nodes that you specified becomes the default node pool. Then you can add additional custom pools of different sizes and types to your cluster. All nodes in any given node pool are going to be identical. And you can also run multiple Kubernetes node versions on each node pool in your cluster and update each node independently, targeting different node pools for specific deployments. So here's what the deployment schema is for, say, a multi-zone default node pool, multi-zone preemptible node pool, and what it looks like. As you can see here, we have a Kubernetes engine running a Kubernetes cluster with a master Kubernetes engine in Zone A. In Zone A, we also see a default node pool, two preemptible node pools, and a PVM-analytics-pool. Notice that the default node pool, one of our preemptible node pools, and our PVM analytics pool has an instance group also in Zone B for high availability. GK's autoscaler is really smart and always tries to first scale the pool with cheaper VMs. That way you don't pay as much money. In this case, it's going to scale up the preemptible node, and the GK autoscaler is then going to scale up the default node pool, but only if no preemptible VMs are available. The cluster autoscaler works on a per node pool basis, and the cluster autoscaler increases or decreases the size of the node pool automatically based on the resource requests of the pods running on that node pool's nodes. It periodically checks the status of the pods and the nodes and takes action automatically. When you configure a node pool with cluster autoscaler, you specify a minimum and a maximum size for the node pool. Now, if pods are unschedulable because there's not enough nodes in the node pool cluster, then autoscaler adds nodes up to the maximum size of the node pool. If nodes are underutilized and all the pods could be scheduled with even fewer nodes in the node pool, then cluster autoscaler is going to remove nodes down to the minimum size of the node pool. If the node cannot be drained gracefully after a timeout period, usually it's about 10 minutes, then the node is forcibly terminated and the grace period is not configurable for GKE clusters. Node auto upgrades help you keep the nodes in your cluster up to date with the cluster master version when your master is updated on your behalf. Node pools with auto upgrades are scheduled for upgrades when they meet the selection criteria announced with release nodes. Now, when you create a new cluster or node pool with Google Cloud Console or the G-Cloud command, Node Auto Update is enabled by default. Node Auto Upgrades provide various benefits such as lower management overhead, better security, ease of use. Auto upgrades ensure that your security updates are kept up to date and provide a simple way to keep your nodes up to date with the latest Kubernetes features. GK's auto repair feature helps you keep the nodes in your clusters in a healthy running state. And when enabled, GK makes periodic checks on the cluster. If the node requires repair, then the node is drained and recreated. If a node fails several consecutive health checks over a period of time, then GK initiates the repair process on that node. Now, if multiple nodes require repair, GK will repair the nodes in parallel and balance the number of repairs depending on the size of the cluster and the number of broken nodes. So there are repair criteria, as you can see. Now, if you disable node auto repair at any time during the repair process, in-progress repairs are not canceled. They will continue for any node currently under repair. Now, using Google Cloud Container Engine Managed Service is a great way to run a Kubernetes cluster with a minimum of management overhead, along with making significant improvements in managing and upgrading your nodes. We wanted to make sure that upgrades are more than a binary operation here. So, frequently, particularly large clusters upgrades, need to be halted, canceled altogether. And Container Engine now supports canceling, rolling back, and continuing upgrades. Kubernetes Engine Monitoring is designed to monitor GKE clusters. It manages monitoring, logging services together with other features. And it features a Kubernetes Engine Monitoring interface that provides a dashboard customized for GKE clusters. Now, the dashboard features a summary pane in which you can view cluster key metrics such as CPU utilization, memory utilization, and the number of open incidents. You can view clusters by their infrastructure, workloads, or services. You can inspect namespaces, nodes, workloads, services, pods, and containers. Now, for pods and containers, you can look at metrics as a function of time. And you can see this in the logs viewer. Kubernetes engine monitoring is priced based on the amount of logs and metrics that are collected. Now, for logging and monitoring, you can use Stackdriver logging to automatically collect, process, and store your container in system logs. Now, this can be integrated with audit logging, and Stackdriver monitoring will monitor your cluster, CPU, and memory, as well as custom metrics for your application. Now, you can retrieve a list of objects using commands like kubectl get pods, which returns a list of all the pods in the cluster. For more information on specifics, of course, you can run the command kubectl describe my pod with a pod name, which gives you detailed information about the pod named, well, my pod name. You can even test and debug, what was in your pod using kubectl exec my pod name in order to execute commands and applications. And the logs command provides powerful tools to see what's happening inside your pod. And logs are always useful in troubleshooting. So let's take a look at troubleshooting Kubernetes engines, beginning with troubleshooting our pods. For an example, let's take an administrator who wants to see a list of pods in the cluster. And after connecting kubectl to the cluster with proper credentials, the administrator can issue the kubectl get pods command. kubectl converts this into an API call, which it's going to send to the kube API server through HTTPS on the cluster's master server. The kube API server processes the request by querying etcd. Kube API server then returns the results to kubectl through HTTPS. And, last but not least, kubectl interprets the API response and displays the results to the administrator at the command prompt. You can also use the kubectl command to view the logs of a pod. If a pod has multiple containers, you can use the minus argument to show the log splitting specific container information inside the pod. The pods contain both standard output and standard error messages that the applications would report from within the container. So let's take a brief quiz on the concepts you've learned so far. Question number 1. A node pool is a group of nodes within a blank that all have the same configuration. If you guessed cluster, then you'd be correct. So here's the next question. Which of the following functions can GKE perform on the nodes? Select 2 of them. Well, if you guessed upgrade and repair, you'd be correct. And finally, true or false, Stackdriver is the tool used to monitor GKE. And the answer is true. So this concludes the Kubernetes on GCP section. In this section, you learned how GKE clusters are powered by Kubernetes open source cluster management system, and Kubernetes provides the mechanisms through which you can interact with your cluster. You can use Kubernetes commands and resources to deploy and manage your applications, perform administration tasks, set policies, and monitor the health of your deployed workloads.